All right, let's jump right in. If you're an AI developer working in speech synthesis, you already know things are moving at lightning speed. Today, we're doing a technical teardown of one of the biggest shifts in the last few years, the VALL family of models. Seriously, this stuff completely changed the game for voice generation.
So here's the big question, right? How on earth can an AI clone a voice from just a tiny 3-second sample? For years, this was a holy grail of zero-shot text-to-speech. But VALL didn't just inch closer to the goal, it took a completely different road to get there. The secret here isn't just about more compute or bigger datasets. It's a fundamental rethink of the entire problem of generating audio.
And this is the core idea. Instead of the old way, trying to predict a continuous audio waveform, VALL reframes the whole thing. It says, what if generating audio is actually a language modeling problem? Just like how GPT generates text. This one conceptual leap right here is what unlocks everything else we're about to get into. So let's break down what this new paradigm actually looks like in practice. We're not talking about a small adjustment here. This is a full-on shift from one engineering philosophy to another. Okay, this table really lays out the revolution perfectly. Traditional TTS models, they work with MEL spectrograms, a continuous signal. But VALL, it uses discrete audio codec codes. Now, this is the key move because it basically turns audio into a vocabulary of tokens. Once you do that, your objective function flips from signal regression to just plain old language modeling. And that's a huge deal because it means VALL can be trained on a mind-boggling 60,000 hours of semi-supervised data. That's 100 times more than usual. The result? Well, you get true in-context learning, the ability to learn a new speaker from a tiny prompt, just like a large language model does with text.
All right, so we've covered the why. Now let's get into the how. Let's pop the hood and see the specific components that make this whole new paradigm actually work.
And this diagram shows the entire data flow, start to finish. Over on the left, you've got your two inputs, the text you wanted to say, and that 3-second audio clip for the voice. The text gets turned into phonemes, and the audio gets crunched down into those discrete tokens we just talked about. Both of those get fed into the core language model, which then predicts a brand new sequence of audio tokens. And finally, a decoder turns those tokens back into an audio waveform. Boom, personalized speech. So, the absolute linchpin of this whole system is the neural audio codec. Think of something like ENCODE. Its job is to take a high-quality audio stream and squash it down into a sequence of discrete tokens at a much, much lower frame rate. This is the magic trick. It's the technical bridge that lets us take all the powerful tools and techniques we've developed for text-based LLMs and apply them directly to the world of audio. So how does the codec actually create these tokens? Well, it uses a process called residual vector quantization, or RVQ. As you can see here, it's a hierarchical thing. The first layer, the first quantizer, captures the big picture stuff, the core of the speaker's voice, the rhythm, the prosody. Then, each layer after that models the residual, basically the error or the stuff that was left over from the layer before it. This lets it add finer and finer details. Separating the coarse from the fine like this is a really critical design choice. VALL takes that clever hierarchical structure and runs with it using a two-stage process. First, an autoregressive, or AR, model predicts the tokens for just that first, most important layer. This gives it the freedom to figure out the timing and rhythm. Then, a non-autoregressive, or NAR, model comes in, takes that base layer, and predicts all the other detail layers all at once, in parallel. It's a really elegant draft and refine pattern that gives you a nice balance between creative control and fast inference speed, a classic engineering trade-off. But of course, the first version wasn't perfect. The evolution of the VALL family is actually a fantastic case study in iterative engineering. Each new model was specifically designed to tackle the problems found in the one before it. First up, you had VALL-X, which took on the cross-lingual challenge. The problem was pretty clear. Could you take my voice, an English speaker, and make me speak fluent Mandarin without a heavy accent? The solution was simple in theory, but just massive in scale. Train the model on a huge multilingual dataset. This let the model learn what a native accent sounds like and then apply it to a new voice, effectively carrying that vocal identity across to a whole new language. The next big problem was robustness. The early models would sometimes, they'd hallucinate. They might repeat words or just skip them entirely. VLI fixed this with a really brilliant technique called monotonic alignment. Instead of just letting the model generate freely, it forces a strict, logical, one-way connection between the input phonemes and the output audio, which dramatically cuts down on those kinds of errors. And these are the 3 rules that make it all work. Locality just keeps the mapping clean. Monotonicity, this is the real game changer. It stops the model from looping back and repeating words. And completeness, make sure it doesn't just decide to skip parts of your text. For any developer out there who's fighting generative drift, this is a powerful pattern to understand. You trade a tiny bit of creative freedom for a massive win in reliability. And finally, VALL 2 set its sights on human parity, which meant tackling stability and speed. The random sampling in the original could sometimes get stuck in these little infinite loops, and the TAR model was still kind of slow. So the solutions were pretty clever. Repetition-aware sampling helps the model intelligently avoid those loops, and grouped code modeling lets the TAR model predict several tokens at once, giving you a really nice speed boost in inference time. Okay, so we've walked through this whole evolution. What's the bottom line for us as developers? What are the key plays we can steal from this playbook and use in our own work? Here are the 5 big ones. 1. Reframing your problem as language modeling can open the door to totally new scales of data. 2. Discrete tokens are your friend. Find the right tokenizer for your domain and you can unlock all those powerful LLM techniques. 3. .AR/NAR hierarchical pattern is a proven winner for balancing quality and speed. 4. If you're doing sequence-to-sequence, enforcing alignment is a powerful tool for making your model more robust. And finally, number 5. Never underestimate how much a smart sampling strategy can improve your model's stability. But you know how it is in this field. Technology never stands still. The story of VALL isn't the final word on the subject. It's just the latest chapter. So, what comes next? What was really fascinating is that one of its successors, a model called Melee, throws a bit of a curveball. It actually moves away from the discrete tokens that got this whole revolution started in the first place. MEL basically swings the pendulum right back. It uses regression loss to generate continuous MEL spectrograms directly, the very thing VALL-E moved away from. But it does it with new tricks, incorporating things like variational inference to get better sampling and more diversity. It just skips quantization entirely, suggesting that maybe the next big leap forward will be some kind of synthesis of these two opposite approaches. And all of this leaves us with a much bigger question, one that goes beyond the code. The engineering is pushing us toward a future where synthetic voices are basically perfect replicas of human ones. As the people building this stuff, it forces us to ask, when a voice can be perfectly cloned, prompted, and transferred across languages, what does vocal identity even mean anymore? It's a question we're all going to have to answer.